The ice lies silent beneath a sky unmarked by cities. It stretches farther than sight, farther than a lifetime of walking could measure. Beneath its weight, the land remembers shapes it will not wear again for tens of thousands of years. Rivers that once moved are frozen into stillness. Forests that stood are gone. The ice has come, and it will stay, and then it will leave, and then it will come again. This has happened before. It will happen again. The rhythm is older than our species, older than the mountains worn smooth beneath the glaciers, older than the bones we dig from the earth to understand what we are and where we came from. If you find yourself drawn into this story, consider watching in full screen. And if it resonates, subscribe to see more. Now, let us begin. The world we live in today, the world of green valleys and temperate coastlines and seasons that shift between warmth and cold, but never trap entire continents beneath miles of ice, is not the world's natural state. It is an intermission, a pause. The pause, a moment of relative warmth inserted between long stretches of cold so profound that ice sheets larger than nations advance over the places we now call home. These intervals of ice, called glaciations, do not arrive randomly. They do not come when the sun flickers or when a mountain erupts. They come with a regularity that, once discovered, seemed almost impossible to believe. Roughly every 100,000 years, the planet's climate tips into a deep freeze. Ice builds. Sea levels fall. Ecosystems retreat toward the equator. And then, after tens of millennia, the ice melts. The oceans rise. Life spreads poleward again, and the cycle repeats. This is not mythology. It is not metaphor. It is a measured, observable fact, written into the layers of the Earth itself, and into the bubbles of ancient air trapped within the ice of Greenland and Antarctica. The discovery of this cycle, the effort to explain it, and the mystery that still surrounds its precise mechanisms form one of the most profound and humbling chapters in the history of science. It is a story that begins not with satellites or supercomputers, but with observers walking through alpine valleys, staring at boulders that had no reason to be where they were, and daring to imagine that the world had once been radically unrecognizably different. In the early 19th century, in the mountains of Switzerland, there were stones that did not belong. They sat on valley floors, far from the peaks where such stones were known to originate. They were enormous, too large to have been carried by rivers, too angular to have been rolled smooth by water. They were scattered in patterns that made no sense unless something immense and powerful had transported them. Local farmers and villagers had long explained these erratic boulders with stories of floods, of biblical deluges that could lift and carry such weights. But a few naturalists began to suspect something else. They looked at the scratches on bedrock, long grooves carved into the stone, as if by something dragging massive weight across the surface. They examined the valleys themselves, their U-shaped profiles, their polished walls, and they began to wonder whether ice, not water, might be responsible. The idea met fierce resistance. The Earth, according to prevailing thought, was a stable and largely unchanging place, sculpted slowly by rivers and seas, not transformed wholesale by advancing sheets of frozen water. To suggest that glaciers, those slow-moving rivers of ice confined to the highest mountains, had once covered lowland Europe was to suggest that the climate itself had undergone catastrophic change. It was to suggest that the past was alien, that the present was temporary, that the future might hold transformations equally vast. Many scientists rejected this. They preferred explanations involving floods or icebergs rafted on floodwaters, or other mechanisms that preserve the notion of a stable Earth. But the evidence kept accumulating. The scratches, called striations, aligned with the direction glaciers would have flowed. The moraines, ridges of debris left at the edges of glaciers, appeared in places far from existing ice. The erratics, those out-of-place boulders, could be traced back to specific source regions in the mountains. And the only plausible agent of transport was ice. One of the key figures in establishing the reality of ice ages was Louis Agassiz, a Swiss naturalist who studied the glaciers of the Alps and became convinced that they had once extended much farther than their present limits. He traveled across Europe, observing landscapes that bore the signature of glacial sculpting. He visited Britain and saw the same features. He crossed the Atlantic and found them in North America. By the mid-19th century, the Ice Age theory, though still controversial, was gaining credibility. The Earth had been cold, ice had advanced, and then it had retreated. But how many times had this happened? And why? The geological record at first offered only fragmentary answers. Evidence of multiple glaciations began to emerge as geologists examined sequences of sediment and till, the unsorted debris left by glaciers. In some places, layers of glacial deposits were separated by layers of soil or peat. suggesting intervals of warmth between ice advances. In others, fossils of cold-adapted and warm-adapted species alternated, indicating that climates had swung back and forth. By the early 20th century, it was clear that there had been not one ice age, but many. The Earth's climate oscillated. But what drove the oscillation? What mechanism could cause the planet to cool so dramatically, then warm again, over and over, with such apparent regularity? One of the first and most enduring answers came from a Serbian mathematician and geophysicist named Dragutin Milanković. In the early 20th century, Milanković became fascinated by the idea that variations in Earth's orbit around the Sun might influence climate. The orbit is not perfectly circular. It is slightly elliptical, and the shape of that ellipse changes over time. A parameter called eccentricity, the tilt of Earth's axis, called obliquity, also varies, shifting between about 22 and 24.5 degrees over a cycle of roughly 41,000 years. And the direction that the axis points, which determines the timing of the seasons relative to Earth's position in its orbit, slowly rotates, a phenomenon called precession, with a cycle of about 26,000 years. Milanković calculated how these three orbital variations would alter the distribution of sunlight across different latitudes and seasons. He found that they could change the amount of solar energy reaching high northern latitudes in summer, and he hypothesized that when that energy was reduced, snow and ice could persist through the summer, reflecting more sunlight, cooling the planet further, and allowing ice sheets to grow. Milanković spent years refining his calculations, producing curves that predicted the timing of ice ages based on orbital cycles. His work was initially met with skepticism. The changes in solar energy he calculated were small, only a few percent. Could such subtle shifts really trigger the massive climatic transformations required to build continental ice sheets miles thick? And the timing, though suggestive, did not perfectly match the fragmentary and uncertain glacial chronologies available in Milanković's era. His ideas were debated, doubted, and at times dismissed, but they were not forgotten. Decades later, in the 1960s and 70s, a revolution in climate science provided the data needed to test Milanković's hypothesis rigorously. Scientists began drilling cores from the seafloor, extracting continuous records of sediment that had accumulated over millions of years. Within those sediments were the shells of tiny marine organisms called foraminifera. These shells are made of calcium carbonate, and the oxygen atoms in that carbonate come from the seawater in which the organisms lived. Oxygen has two stable isotopes, oxygen-16 and oxygen-18. The ratio of these isotopes in seawater changes depending on how much water is locked up in ice sheets. When ice sheets grow, they preferentially trap the lighter isotope, oxygen-16, leaving the oceans enriched in the heavier oxygen-18. When the ice melts, the ratio shifts back. By measuring the oxygen isotope ratios in foraminifera shells from successive layers of seafloor sediment, scientists could reconstruct a history of ice volume on Earth stretching back millions of years. What they found was astonishing. The isotope record revealed a clear repetitive pattern. Over the past million years or so, ice sheets had grown and melted in cycles that matched, with remarkable precision, the predictions of Milanković's orbital theory. But there was a twist. The dominant cycle in the data was not the 41,000-year obliquity cycle, nor the 26,000-year precession cycle, but a cycle of roughly 100,000 years. This was the period of the eccentricity cycle, the slow change in the shape of Earth's orbit. Yet eccentricity of all the orbital parameters had the smallest direct effect on the amount of sunlight reaching Earth. It modulated the other cycles, amplifying or dampening their effects, but it should not, by itself, have been the dominant signal. And yet it was. This discrepancy became known as the 100,000-year problem, and it remains one of the most intriguing unsolved questions in climate science. Before delving deeper into that mystery, it is worth pausing to appreciate the sheer scale and detail of the evidence that supports the reality of these cycles. The oxygen isotope record from ocean sediments is just one line of evidence, though it is among the most continuous and precise. Ice cores, drilled from the interiors of Greenland and Antarctica, provide another. These cores are cylinders of ice extracted from depths of several kilometers, and they contain layers that represent hundreds of thousands of years of snowfall. Each layer captures a snapshot of the atmosphere at the time the snow fell, bubbles of ancient air are trapped within the ice, preserving samples of the atmosphere's composition. By analyzing the gases in those bubbles, scientists can measure past concentrations of carbon dioxide, methane, and other greenhouse gases. By measuring the isotopes of hydrogen and oxygen in the ice itself, they can infer past temperatures. The ice cores from Antarctica extend back more than 800,000 years, and they reveal a climate that has oscillated repeatedly between cold glacial periods and warmer interglacials with a rhythm that mirrors the ocean sediment record. The agreement between ice cores and ocean sediments, two entirely independent archives, is a powerful confirmation of the reality of these cycles. But the evidence does not stop there. On land, the traces of past glaciations are carved into the landscape. Valleys that were once filled with ice now hold rivers that seem too small to have shaped them. These U-shaped valleys, with their steep sides and flat floors, are the signature of glacial erosion. Moraines, ridges of rock and soil pushed up by advancing glaciers, mark the farthest extent of past ice sheets. Drumlins, elongated hills shaped by the flow of ice over sediment, are scattered across regions that were once glaciated. Eskers, winding ridges of sand and gravel deposited by meltwater rivers flowing beneath or within glaciers, snake across the landscape. Each of these features is a remnant of fossil of ice. In addition to these physical landforms, there are chemical and biological signatures. Pollen grains preserved in lake sediments and peat bogs tell us which plants grew in which places at which times during glacial periods. Pollen from cold-adapted species like spruce and tundra grasses dominates. During interglacials, pollen from temperate species like oak and elm appears. The distribution of these species shifted dramatically as the climate changed, with entire ecosystems migrating hundreds or thousands of kilometers. Animal fossils tell similar stories. Woolly mammoths and woolly rhinoceroses roamed Europe and North America during glacial times, then vanished as the climate warmed. Coral reefs, which grow only in warm, shallow seas, shifted their ranges as sea levels and temperatures changed. Sea level itself is one of the most dramatic indicators of glacial cycles. When ice sheets grow, they lock up water that would otherwise be in the oceans. During the peak of the last glacial period, about 20,000 years ago, global sea level was roughly 120 meters lower than it is today. Coastlines were radically different. Land bridges connected regions now separated by water. The islands of Southeast Asia were joined to the mainland. Britain was connected to Europe. The Bering Strait, which now separates Alaska from Siberia, was dry land, a wide plain across which humans and animals migrated. Evidence of these lower sea levels is preserved in drowned river valleys, submerged coastlines, and coral reefs that grew when sea level was lower and are now found far below the surface. All of these lines of evidence converge on the same conclusion. Earth's climate has oscillated between glacial and interglacial states for millions of years, and over the past roughly 1 million years, the dominant cycle has been close to 100,000 years. The ice advances, the ice retreats, the pattern repeats. But understanding that the pattern exists is not the same as understanding why it exists. The discovery of the cycle raised as many questions as it answered. What triggers the transition from warm to cold? What triggers the reverse? Why does a cycle take 100,000 years and not 50,000 or 200,000? And what does this mean for the present, for the current interglacial period in which we live, and for the future in which human activity is altering the composition of the atmosphere at a pace and scale unprecedented in the geological record? To begin answering these questions, it is necessary to understand how small changes in sunlight can produce large changes in climate. The orbital variations calculated by Milankovitch change the distribution of sunlight across the planet, but they do not change the total amount of sunlight Earth receives by much. The changes are subtle, a few percent at most in specific seasons and latitudes. Yet the climate response is anything but subtle. Ice sheets kilometers thick advance and retreat. Global temperatures swing by several degrees Celsius. Carbon dioxide concentrations in the atmosphere change by tens of parts per million. These large responses to small forcings are possible because of feedback mechanisms, processes that amplify an initial change. The most straightforward feedback involves ice and snow themselves. Ice and snow are highly reflective. They have a high albedo, meaning they reflect a large fraction of incoming sunlight back into space. When ice sheets grow, they increase the planet's albedo, reducing the amount of solar energy absorbed by the surface, which cools the climate further, allowing more ice to form. This is the ice albedo feedback, and it is a positive feedback, meaning it amplifies the initial change. Conversely, when ice melts, the exposed land or ocean absorbs more sunlight, warming the climate further, accelerating the melting. This feedback alone can amplify the effects of orbital variations significantly, but ice albedo feedback is not the only mechanism at work. The ocean plays a crucial role. The ocean is a vast reservoir of carbon containing far more carbon than the atmosphere. The exchange of carbon dioxide between the ocean and the atmosphere depends on temperature, circulation, and biological activity. When the climate cools, the solubility of carbon dioxide in seawater increases, allowing the ocean to absorb more carbon dioxide from the atmosphere. At the same time, changes in ocean circulation can affect the upwelling of deep water, which brings carbon-rich water to the surface, and changes in the productivity of marine life can alter the rate at which carbon is transported to the deep ocean and locked away in sediments. During glacial periods, atmospheric carbon dioxide concentrations are lower, around 180 parts per million, compared to roughly 280 parts per million during interglacials. This reduction in carbon dioxide, a potent greenhouse gas, amplifies the cooling initiated by orbital changes. The precise mechanisms that drive this carbon cycle feedback are still being studied. It is likely that multiple factors are involved, including changes in the biological pump, the process by which marine organisms take up carbon and transport it to the deep ocean, changes in ocean circulation driven by shifts in wind patterns and the formation of sea ice, and changes in the alkalinity and chemistry of seawater. The important point is that the climate system is interconnected. Ice, atmosphere, ocean, and life all influence one another. A small initial change in one component can trigger responses in others, and those responses can feed back to amplify the original change. There are other feedbacks as well. Water vapor, the most abundant greenhouse gas, increases in a warmer atmosphere and decreases in a cooler one, amplifying both warming and cooling. Changes in vegetation alter the surface albedo and the exchange of carbon dioxide between the land and atmosphere. Dust blown from exposed continental shelves and deserts during glacial periods can fertilize the ocean, enhancing biological productivity and carbon uptake, or it can settle on ice, darkening it and reducing its albedo. Each of these processes adds complexity to the system, and each can contribute to the large climate swings observed in the geological record. But even with all these feedbacks, the 100,000-year problem remains. Why does the eccentricity cycle, which has the smallest direct effect on sunlight, dominate the glacial record? One possibility is that the ice sheets themselves introduce a nonlinearity, a threshold, or time-dependent behavior that creates a strong 100,000-year rhythm even when the direct forcing at that frequency is weak. Ice sheets do not grow and melt instantaneously. They respond slowly to changes in climate, taking thousands of years to build up and thousands of years to decay. The dynamics of ice sheets are complex, involving processes like ice flow, calving of icebergs, interactions with the underlying bedrock, and changes in the properties of the ice itself as it ages and compresses. One influential idea is that ice sheets can become unstable once they reach a certain size. As an ice sheet grows, it depresses the underlying bedrock, a process called isostatic adjustment. The ice also thickens, and at some point, the base of the ice may warm due to the insulating effect of the ice above and the geothermal heat from below. Warm ice flows more easily than cold ice, and if the base of the ice sheet reaches the melting point, the ice can begin to slide more rapidly over the bedrock or over a layer of meltwater. This can lead to a sudden acceleration in ice flow, thinning the ice sheet and exposing it to warmer air, which accelerates melting. Such instabilities could cause ice sheets to collapse more rapidly than they grow, creating an asymmetry in the glacial cycle. The slow buildup of ice over tens of thousands of years could be followed by a relatively rapid melt over a few thousand years, a pattern that is indeed observed in the isotope records, where glacial periods tend to end with abrupt warming events called terminations. Another factor that may contribute to the 100,000-year cycle is the interaction between different ice sheets. During glacial periods, ice sheets grew not only in Antarctica, which is always glaciated, but also over large parts of North America and Eurasia. The Laurentide ice sheet, which covered much of Canada and the northern United States, and the Fennoscandian ice sheet, which covered Scandinavia and parts of northern Europe, were massive. Their growth and decay were not perfectly synchronized, and interactions between them mediated by changes in ocean circulation. Atmospheric circulation and sea level could introduce complex timing that resonates with the eccentricity cycle. Some researchers have proposed that the 100,000-year cycle emerges from a combination of the obliquity and precession cycles, rather than directly from eccentricity. The idea is that the ice sheets respond to forcing at the obliquity and precession periods, but because of their slow response and internal dynamics, they integrate or skip certain cycles, producing a longer effective period. This is analogous to a physical system that has a natural resonance frequency and responds strongly to certain forcing frequencies while filtering out others. The climate system with its ice sheets, oceans, and feedbacks may have properties that make it resonate at roughly 100,000 years. Another line of investigation focuses on the role of carbon dioxide. As mentioned, atmospheric carbon dioxide concentrations vary in lockstep with temperature and ice volume over glacial cycles, but the mechanisms that control these carbon dioxide changes are not fully understood. If changes in carbon dioxide are a response to temperature, driven by changes in ocean chemistry and biology, then they act as a feedback, amplifying orbital forcing. But if there are processes that cause carbon dioxide to change on a 100,000-year timescale, independently of orbital forcing, then carbon dioxide could drive the cycle rather than merely respond to it. Some researchers have speculated about long-term changes in ocean circulation, volcanic activity, or even the weathering of rocks, which consumes carbon dioxide, but these ideas remain speculative. The 100,000-year problem is not merely an academic curiosity. It reflects a deeper uncertainty about how the climate system works, about which processes are most important in driving large climate changes, and about how stable or unstable the climate is in the face of perturbations. Understanding this is crucial for interpreting past climate changes and for predicting future ones. The present is a test case. Human activity, primarily the burning of fossil fuels, has increased atmospheric carbon dioxide concentrations from the pre-industrial level of about 280 parts per million to over 400 parts per million, a level not seen on Earth for at least several million years, long before the current pattern of glacial cycles began. This rapid increase is driving global warming, melting ice, raising sea levels, and altering ecosystems, but it is also inadvertently interfering with the natural glacial cycle. Based on orbital parameters, some models suggest that the current interglacial, which began about 11,700 years ago, should eventually give way to a new glacial period. The timing is uncertain, with estimates ranging from thousands to tens of thousands of years in the future. But the massive injection of carbon dioxide into the atmosphere by human activity is likely to delay or even prevent the next glaciation. Elevated greenhouse gas concentrations will keep the planet warmer than it would otherwise be, preventing the initial cooling needed for ice sheets to grow. In essence, human activity may be extending the current interglacial, postponing the return of the ice. This is not necessarily a benign intervention. The current interglacial climate, though warmer than a glacial period, is the climate in which human civilization developed. It is the climate to which our agriculture, infrastructure, and societies are adapted. Pushing the climate into a state warmer than any interglacial in the past, several 100,000 years, brings its own risks, including more extreme weather. Shifts in precipitation patterns, loss of biodiversity, and sea level rise that could continue for centuries or millennia as ice sheets slowly respond to the warming. The interplay between natural orbital cycles and human-driven climate change is one of the most striking aspects of our current moment in Earth history. For the vast majority of the past several million years, climate has been governed by the rhythms of Earth's orbit, modulated by feedbacks involving ice, ocean, and atmosphere. Now, for the first time, a single species is exerting an influence on the climate system that rivals or exceeds the natural forcings. This does not mean that the orbital cycles have ceased to exist or that they will not influence climate in the future. It means that their effects are being masked or delayed by a much larger and more rapid forcing. Understanding the natural cycles is essential for understanding what we are perturbing and what the long-term consequences might be. Returning to the Ice Age cycle itself, it is useful to consider the specific sequence of events during a typical glacial cycle, drawing on the detailed records available from the most recent cycles. The last glacial period, often referred to as the last glacial maximum, when ice was at its greatest extent around 20,000 years ago, provides a particularly well-studied example. The descent into that glacial period began roughly 115,000 years ago, at the end of the previous interglacial known as the Eemian or the last interglacial. The Eemian was similar in many ways to the current interglacial, the Holocene. It was warm, perhaps even slightly warmer than the Holocene at its peak, with forests extending into high latitudes and sea levels possibly a few meters higher than today due to melting of the Greenland and possibly parts of the West Antarctic ice sheets. The transition out of the Eemian and into the last glacial period was gradual, driven by changes in orbital parameters that reduced summer insolation in the northern hemisphere. As summers became cooler, snow and ice that fell during winter began to persist through the summer in high latitudes and high elevations. Over time, this snow accumulated, compacted into ice, and began to flow outward under its own weight, forming the beginnings of ice sheets. The growth was not smooth or uniform. The climate varied on shorter timescales, with periods of rapid cooling and warming superimposed on the longer trend toward glaciation. These variations, visible in ice cores and ocean sediments, reflect complex interactions within the climate system, including changes in ocean circulation and the release or uptake of greenhouse gases. One of the most striking features of glacial periods is the presence of abrupt climate events, rapid swings in temperature, and other climate variables that occurred over decades or centuries, much faster than the orbital timescales. These events, known as Dansgaard-Oeschger events in the ice core record and as Heinrich events in the ocean sediment record, are not fully understood but are thought to involve changes in the circulation of the North Atlantic Ocean and the behavior of the ice sheets surrounding it. During Heinrich events, massive amounts of icebergs were released into the North Atlantic, probably from the Laurentide ice sheet. These icebergs carried debris that settled on the seafloor, leaving distinctive layers of ice-rafted detritus and ocean sediments. The influx of fresh water from melting icebergs would have altered ocean salinity and density, potentially disrupting the Atlantic meridional overturning circulation, a system of ocean currents that transports heat from the tropics to the North Atlantic. Weakening this circulation would have cooled the North Atlantic region, affecting climate across a wide area. Dansgaard-Oeschger events, by contrast, are characterized by rapid warming in the North Atlantic followed by gradual cooling. They recur roughly every 1,500 years during glacial periods, though the mechanism that sets this pacing is unknown. These events show that the glacial climate was highly variable, capable of shifting between states on timescales much shorter than the orbital cycles. This variability may reflect the presence of multiple stable states or modes of the climate system, with transitions between states triggered by relatively small perturbations. The existence of such abrupt events is a reminder that the climate system is not a simple, smoothly varying system, but one with thresholds, tipping points, and feedbacks that can produce rapid and large responses. As the last glacial period progressed, ice sheets reached their maximum extent around 20,000 years ago. At this time, the Laurentide ice sheet covered an area of roughly 13 million square kilometers, with ice more than 3 kilometers thick in places. The Fennoscandian ice sheet covered a similar area in northern Europe. The Antarctic ice sheet expanded, though not as dramatically as the northern hemisphere ice sheets, because Antarctica was already mostly ice-covered and surrounded by ocean. Smaller ice caps and glaciers formed in mountainous regions around the world. The total volume of ice on land was roughly 50 million cubic kilometers greater than today, locking up enough water to lower global sea level by about 120 meters. The world during the last glacial maximum was starkly different from today. Much of Canada, the northern United States, Scandinavia, and northern Asia were buried under ice. The climate was colder and drier. Atmospheric carbon dioxide was at its glacial low of around 180 parts per million. Vegetation zones were shifted toward the equator. Tropical rainforests were reduced in extent, replaced in part by savanna and grassland. Deserts expanded. The exposed continental shelves, dry because of low sea level, were often barren or covered in tundra. The amount of dust in the atmosphere was much higher, blown from these exposed and sparsely vegetated surfaces, and this dust is recorded in ice cores as a distinctive signal of glacial conditions. The termination of the last glacial period, the transition back to the current interglacial, began around 19,000 years ago and was largely complete by about 11,700 years ago, marking the beginning of the Holocene. This termination, like others in the geological record, was relatively rapid compared to the slow buildup of ice. It was not a smooth transition, but occurred in a series of steps, with periods of warming interrupted by brief cold reversals. One such reversal, known as the Younger Dryas, occurred around 12,800 to 11,700 years ago. During the Younger Dryas, temperatures in the North Atlantic region dropped sharply, approaching near glacial conditions, even as the overall trend was toward warming. The cause of the Younger Dryas is debated, but a leading hypothesis involves a sudden influx of fresh water into the North Atlantic, possibly from the drainage of a large glacial lake as the ice sheets retreated, which disrupted ocean circulation and caused regional cooling. The end of the Younger Dryas was abrupt, with temperatures in Greenland rising by several degrees Celsius in just a few decades. This rapid warming marked the final transition into the Holocene, the warm interglacial period in which we still live. The Holocene has been relatively stable compared to the glacial period that preceded it. Temperatures have varied, with periods slightly warmer or cooler than the long-term average, but there have been no abrupt shifts comparable to those of the glacial period. This stability has allowed human societies to develop agriculture, settle in permanent communities, build cities, and create complex civilizations. It is no coincidence that all of recorded human history falls within the Holocene. The relatively stable and warm climate of the interglacial provided the conditions necessary for the development of modern human society. But the Holocene is itself an interglacial, a temporary warm period within the longer glacial cycle. The orbital parameters that favored warmth at the end of the last glacial period have changed. Northern Hemisphere's summer insolation, which was high around 11,000 years ago, has been gradually declining. By itself, this decline should favor a slow cooling and the eventual growth of ice sheets. However, atmospheric carbon dioxide concentrations, which naturally varied between about 180 and 280 parts per million over glacial interglacial cycles, began to rise again around 8,000 years ago, a time when orbital forcing would have been expected to cause a slight decline. Some researchers have suggested that this rise was due to early agricultural activities, including deforestation and rice cultivation, which released carbon dioxide and methane. This hypothesis, known as the early anthropogenic hypothesis, is controversial, but it raises the intriguing possibility that human influence on climate began not in the industrial era, but thousands of years earlier, and that this influence may have prevented the climate from cooling as it otherwise would have. Regardless of when human influence began, there is no doubt that the industrial era has brought a dramatic acceleration in greenhouse gas emissions. The burning of coal, oil, and natural gas, combined with deforestation and industrial agriculture, has driven atmospheric CO2 from about 280 parts per million in the pre-industrial era to over 400 parts per million today, with concentration still rising. Methane and nitrous oxide, other potent greenhouse gases, have also increased. The warming effect of these gases is measurable and attributable to human activity. Global average temperatures have risen by roughly 1 degree Celsius since the late 19th century, and the rate of warming is accelerating. Ice sheets in Greenland and Antarctica are losing mass. Glaciers around the world are retreating. Sea levels are rising, both because warming water expands and because melting ice adds water to the oceans. Ecosystems are shifting, with species migrating toward the poles or to higher elevations, and with some species facing extinction because they cannot migrate fast enough or because suitable habitat no longer exists. In the context of the glacial cycle, the current warming is unusual not because warming is unusual. Interglacial periods are warm by definition, but because the rate and magnitude of warming exceed anything seen in the Holocene or in previous interglacials as far back as the ice core record extends. The rapid rise in carbon dioxide is particularly striking. During natural glacial-interglacial transitions, carbon dioxide rose by about 100 parts per million over several thousand years. In the past 250 years, it has risen by more than 130 parts per million, and the rate of increase is currently about 2 to 3 parts per million per year, roughly 100 times faster than the natural rate during deglaciations. This rapid increase is driving the climate out of the range of natural variability experienced during the glacial cycles of the past million years. Models project that if greenhouse gas emissions continue at current or higher rates, global temperatures could rise by several degrees Celsius over the coming century, a warming that would exceed the typical interglacial warmth and approach or surpass the warmth of periods millions of years ago, such as the Pliocene, when the climate was substantially different and sea levels were tens of meters higher. Even if emissions are reduced and warming is limited to the lower end of projected ranges, the climate will remain warmer than the Holocene average for many centuries because carbon dioxide remains in the atmosphere for a long time, and because the ocean and ice sheets respond slowly to changes in atmospheric composition. The implications for the natural glacial cycle are profound. The orbital cycles that have paced ice ages for millions of years are still operating. Earth's orbit continues to evolve according to the laws of celestial mechanics, but the climate response to those orbital changes is being overwhelmed by the much larger forcing from greenhouse gases. In the absence of human influence, the current interglacial might last for several more tens of thousands of years before the next glaciation begins, or it might be shorter, depending on the precise configuration of orbital parameters and the timing of internal climate feedbacks. But with atmospheric carbon dioxide elevated to levels far above the natural interglacial range, and with continued emissions projected for decades to come, the next glaciation is likely to be delayed by tens or even hundreds of thousands of years. Some modeling studies suggest that the current anthropogenic warming could prevent the next several glaciations, effectively skipping multiple cycles of the natural rhythm. This does not mean that the Ice Age cycle is permanently broken. If human greenhouse gas emissions were to cease, and if natural processes were to remove the excess carbon dioxide from the atmosphere, a process that would take many thousands of years for the atmosphere to return to pre-industrial levels and much longer for the deep ocean to equilibrate, then the orbital cycles could eventually reassert their influence. But on the timescales relevant to human societies, the next tens of thousands of years, the climate will be shaped far more by what humans do than by the slow variations in Earth's orbit. We are, in effect, living in a new climatic regime, one in which human activity is the dominant driver of climate change, superimposed on the natural cycles that have governed climate for millions of years. Understanding the Ice Age cycle, the mechanisms that drive it, and the feedbacks that amplify it is therefore not an exercise in studying the distant past or an abstract future. It is directly relevant to understanding the present and the future. The same feedbacks that amplified orbital forcing during glacial cycles are operating now, amplifying human-caused warming. The ice albedo feedback is operating in reverse, with melting ice reducing Earth's albedo and accelerating warming. The carbon cycle feedbacks are operating, with warming oceans and thawing permafrost potentially releasing additional carbon dioxide and methane, further enhancing warming. The water vapor feedback is operating, amplifying the warming caused by long-lived greenhouse gases. Understanding these feedbacks, their magnitudes, and their timescales is essential for predicting how much warming will occur and how long it will persist. The Ice Age cycle also provides a benchmark for understanding the sensitivity of the climate system. Climate sensitivity is a measure of how much the climate warms in response to a given increase in radiative forcing, such as from increased IoT. By studying past climate changes and the forcings that drove them, scientists can estimate climate sensitivity, the glacial-interglacial transitions driven by orbital changes and amplified by feedbacks provide a natural experiment. The amount of warming from a glacial to an interglacial, the changes in carbon dioxide and other greenhouse gases, the changes in ice cover and other factors all provide constraints on climate sensitivity. These constraints generally agree with estimates from climate models and from observing the response of the current climate to recent increases in greenhouse gases, all pointing to a climate sensitivity of around 3 degrees Celsius warming for a doubling of carbon dioxide, with a range of uncertainty that extends from roughly 2 to 4.5 degrees Celsius. This means that the warming we are already committed to from the CO2 already in the atmosphere is substantial, and additional emissions will drive further warming. The long timescales of the natural glacial cycle also remind us that climate changes persist. The ice sheets that grew during glacial periods took tens of thousands of years to build and thousands of years to melt. The carbon dioxide released into the atmosphere by human activity will remain there for millennia, and the warming it causes will persist long after emissions cease. The ocean will continue to warm, ice sheets will continue to lose mass, and sea levels will continue to rise for centuries even if greenhouse gas concentrations are stabilized. The climate system has inertia. It does not respond instantly to changes in forcing, and it does not return instantly to a previous state when forcing is removed. The geological record of glacial cycles also reveals that climate can change abruptly, not just gradually. The abrupt events during glacial periods, the Dansgaard-Oeschger events and Heinrich events, show that the climate system has tipping points, thresholds beyond which it can shift rapidly into a different state. These events were regional, primarily affecting the North Atlantic and surrounding areas, but they demonstrate that the climate system is capable of surprises. There is concern that future warming could trigger similar abrupt changes, such as a collapse of the Atlantic meridional overturning circulation, a rapid disintegration of parts of the Antarctic or Greenland ice sheets, or a large-scale release of methane from thawing permafrost or marine sediments. These are low probability but high consequence events, and their possibility underscores the importance of understanding the climate system and avoiding pushing it too far from the range of conditions it has experienced in the recent geological past. Another lesson from the glacial cycles is the interconnectedness of the Earth system. The cycles involve interactions between the solid Earth, the ice sheets, the oceans, the atmosphere, and the biosphere. Changes in one component affect others. The growth of ice sheets depresses the crust, altering the Earth's shape and gravitational field. Melting ice raises sea level, flooding coastal areas and altering ocean circulation. Changes in vegetation alter the carbon cycle and the surface albedo. Dust blown from deserts fertilizes the ocean, affecting marine life and carbon uptake. Volcanic eruptions inject aerosols into the atmosphere, temporarily cooling the climate. Cosmic rays, modulated by changes in the solar wind and the Earth's magnetic field, may influence cloud formation, though this effect is highly uncertain and controversial. Each of these processes operates on its own timescale, and they interact in complex ways. Understanding the glacial cycles requires understanding this complexity, and it requires piecing together evidence from many different sources, each providing a different window into the past. The work of reconstructing past climates, a field known as paleoclimatology, is painstaking and incremental. It involves drilling ice cores in the most remote and inhospitable places on Earth, extracting sediment cores from the deep ocean floor, mapping glacial landforms, collecting and analyzing fossils, measuring isotopes in rocks and minerals, and building and testing models that simulate the climate system. Each measurement, each data point, is a small piece of a vast puzzle. Over decades, thousands of scientists working in dozens of countries have assembled a picture of Earth's climate history that is detailed, coherent, and astonishing in its scope. The Ice Age cycle is one of the central features of that picture, a recurring pattern that has shaped the planet for millions of years, and that continues to shape it today, even as human activity introduces a new and powerful force. The glacial cycles of the past million years are part of a longer history of climate change on Earth. The roughly one-nighted 1,000-year cycle that dominates the recent record is itself a relatively recent development. Going back further in time, to between about 2.5 million and 1 million years ago, glacial cycles were present, but they were shorter, with a dominant period of around 41,000 years, matching the obliquity cycle. This is called the 40,000-year world, and it represents a different mode of glacial cycling. The transition from the 40,000-year world to the 100,000-year world around 1 million years ago is called the mid-Pleistocene transition, and it is another major unsolved problem in climate science. What changed at that time to make the climate system start oscillating with a longer period? Several hypotheses have been proposed. One is that the ice sheets gradually became larger and more stable, allowing them to persist through multiple obliquity cycles and to respond more strongly to the weaker eccentricity forcing. Another is that there was a long-term decline in atmospheric carbon dioxide, making the climate cooler overall and allowing ice sheets to grow larger. Another possibility involves changes in the regolith, the layer of loose rock and sediment on which ice sheets rest. As glaciers advanced and retreated over millions of years, they eroded the bedrock and removed the regolith, leaving a harder, less erodible surface that could support larger, more stable ice sheets. Each of these hypotheses has some support, and it is possible that multiple factors contributed. Going back even further, before the current ice age, defined as the period of recurring glaciations over the past few million years, Earth's climate was generally warmer. During much of the past 50 million years, there were no large ice sheets at all, even at the poles. Antarctica was forested. The Arctic Ocean was warm enough for palm trees to grow on its shores. This was a greenhouse world, with carbon dioxide concentrations much higher than today, possibly 1,000 parts per million or more. The transition from that warm world to the current ice age began around 34 million years ago with the formation of the Antarctic ice sheet, and it was driven by a long-term decline in atmospheric carbon dioxide side P, C to D. That decline, in turn, was likely caused by changes in plate tectonics, volcanic activity, and the weathering of rocks, which remove carbon dioxide from the atmosphere. The opening of oceanic gateways, such as the Drake Passage between South America and Antarctica, altered ocean circulation and helped isolate Antarctica, allowing it to cool and accumulate ice. Later, around 2.5 million years ago, ice sheets began to form in the northern hemisphere, marking the beginning of the Pleistocene glaciations and the glacial cycles that have dominated the climate ever since. This longer view shows that the current ice age, with its glacial interglacial cycles, is a temporary state in Earth's history. On timescales of tens of millions of years, the climate is shaped by plate tectonics, which alters the distribution of land and ocean, the positions of mountain ranges, and the rate of volcanic outgassing of carbon dioxide. On shorter timescales, millions of years, the climate is shaped by the carbon cycle, the slow cycling of carbon between rocks, the ocean, the atmosphere, and life. On the timescales of the glacial cycles, tens to hundreds of thousands of years, the climate is shaped by orbital variations and feedbacks. And on even shorter timescales, decades to centuries, the climate can be shaped by volcanic eruptions, variations in solar output, and now by human activity. Each of these timescales is relevant to understanding climate, and each provides context for understanding the others. The Ice Age cycle, with its 100,000-year rhythm, is thus one chapter in a much longer story. But it is a chapter that is particularly relevant to understanding the present, because it is the most recent, because the evidence for it is the most detailed and accessible, and because the mechanisms that drive it, the feedbacks that amplify it, and the abrupt changes that punctuate it are all operating now. The difference is that now, for the first time, there is a species on Earth that is aware of these cycles, that can study them, and that has the power to perturb them. This is a unique moment in Earth's history. For millions of years, the climate cycled according to the rhythms of the orbit and the internal dynamics of the Earth system, unobserved and unaffected by life, even though life was profoundly affected by it. Now, a single species has gained the ability to alter the climate on a scale that rivals the natural forces that have shaped it. This realization is relatively recent. The Ice Age theory itself was not widely accepted until the mid-19th century. The role of carbon dioxide in regulating climate was proposed in the late 19th century by scientists like Svante Arrhenius, who calculated that doubling carbon dioxide could warm the planet by several degrees. But it was not until the mid-20th century that measurements of atmospheric carbon dioxide began, starting with the work of Charles Keeling at Mauna Loa Observatory in Hawaii, and not until the late 20th century that the global extent and pace of warming became clear. The recognition that human activity could alter the glacial cycle came even later, emerging from modeling studies and paleoclimate research in the late 20th and early 21st centuries. The story of the Ice Age cycle is therefore not just a story about Earth's past, but also a story about the development of human understanding, the growth of science, and the realization of our place in the Earth system. It is a story that involves field observations by geologists, laboratory measurements by chemists, calculations by physicists, drilling and engineering by technologists, and synthesis by climatologists. It is a collaborative, cumulative effort that spans continents and generations, and it is a story that is still unfolding. There are still uncertainties, still questions, still debates. The 100,000-year problem is not fully solved. The precise mechanisms that trigger deglaciations are not fully understood. The likelihood and consequences of abrupt climate changes in the future are difficult to predict. The long-term trajectory of human-driven climate change and its interactions with the natural glacial cycle are uncertain. But the broad outlines of the story are clear. Earth's climate oscillates between glacial and interglacial states on timescales of tens of thousands of years, driven by variations in Earth's orbit and amplified by feedbacks involving ice, carbon dioxide, and other components of the climate system. These cycles have been operating for millions of years. We live in an interglacial, a warm period that has allowed human civilization to develop. That interglacial would eventually end, giving way to a new glaciation. But human activity is now warming the planet at a rate and to a level that will likely delay or prevent the next glaciation. This is not a cause for completion. The warming we are causing brings its own risks, different from but no less significant than those of a glacial period. Understanding the natural cycles helps us understand what we are changing and what the consequences might be. The ice itself, that vast accumulation of frozen water that defines a glacial period, is not merely a passive archive of climate history. It is an active agent in the climate system. Its weight deforms the Earth's crust. Its bright surface reflects sunlight. Its melting releases fresh water that alters ocean circulation. Its flow carves landscapes and transports sediment. The ice sheets that covered North America and Europe during the last glacial period were kilometers thick, containing enough ice to lower sea level by over 100 meters. The forces involved in their growth and decay are immense. The advance of an ice sheet can scour away soil and vegetation, grind down bedrock, and bulldoze vast quantities of sediment. The retreat of an ice sheet can flood river valleys, create new lakes, and leave behind a landscape of moraines, eskers, drumlins, and other distinctive landforms. The speed at which ice sheets advance and retreat varies. The growth of ice sheets is generally slow, limited by the rate at which snow can accumulate and compact into ice. In high latitudes, snowfall rates are often modest, and it can take thousands of years for an ice sheet to grow to its full extent. The retreat can be faster, especially if melting is enhanced by rising temperatures, or if the ice sheet becomes unstable and begins to disintegrate. The last deglaciation, the melting of the great ice sheets that covered the northern hemisphere, was not uniform. There were periods of rapid melting punctuated by pauses, or even brief re-advances. These variations are recorded in the sediments and landforms left behind, and they provide clues to the mechanisms of deglaciation. One of the most dramatic aspects of deglaciation is the release of meltwater. As ice sheets melt, they produce vast quantities of water that must flow somewhere. This water carves channels, deposits sediment, and can form large proglacial lakes, lakes dammed by the ice or by moraines. Some of these lakes were enormous. Lake Agassiz, which formed in front of the retreating Laurentide ice sheet in what is now central North America, covered an area larger than any modern lake, except the Caspian Sea. As the ice sheet retreated, the outlets of Lake Agassiz shifted, and at times, large volumes of water were suddenly released as ice dams broke or as new drainage routes opened. These floods, sometimes called jokolaps, a term borrowed from Icelandic, could be catastrophic, carving deep channels and carrying massive boulders. They also had climate effects. The sudden influx of fresh water into the North Atlantic could disrupt ocean circulation, as is thought to have happened during the Younger Dryas-Cold reversal. The memory of these meltwater floods is preserved not only in geological features, but also in sediment cores from the ocean. During periods of rapid melting, the oxygen isotope ratios in ocean sediments shift as meltwater, enriched in the lighter isotope, enters the ocean. The layers of ice-rafted debris deposited during Heinrich events mark episodes when large numbers of icebergs, loaded with rock debris from the ice sheet, drifted into the ocean and melted, dropping their cargo onto the seafloor. These layers are evidence of instability in the ice sheets, moments when ice was discharging into the ocean much faster than normal. The dynamics of ice sheets are governed by the physics of ice flow. Ice is a solid, but over long timescales, it behaves like a very viscous fluid, flowing under its own weight. The rate of flow depends on the temperature of the ice, the thickness of the ice sheet, the slope of the underlying bedrock, and the properties of the material beneath the ice. Ice flows faster when it is warmer because warm ice is softer. It flows faster when it is thicker because thicker ice exerts more pressure. It flows faster over smooth bedrock or over sediment that can deform, and it flows much faster if there is liquid water at the base because the water acts as a lubricant, reducing friction. The presence of water at the base of an ice sheet is crucial to understanding its behavior. Water can be produced by melting at the base due to geothermal heat or due to the pressure of the ice itself, which lowers the melting point. Water can also reach the base from the surface if crevasses or channels allow meltwater to drain downward. Once water is present at the base, the ice can slide over the bedrock, a process called basal sliding, which is much faster than the internal deformation of ice. Basal sliding is thought to be important in the dynamics of ice streams, fast-flowing regions within ice sheets that transport large volumes of ice toward the margins. Ice streams can be tens or hundreds of kilometers wide and can flow at speeds of hundreds of meters per year, much faster than the surrounding ice. Understanding ice streams and their behavior is critical for predicting the future of ice sheets. The Greenland and Antarctic ice sheets are currently losing mass, and much of that loss is occurring through ice streams and outlet glaciers that drain ice into the ocean. If these ice streams accelerate, the rate of mass loss will increase, contributing to sea level rise. The mechanisms that control ice stream flow are complex and not fully understood. They involve interactions between the ice, the bedrock, the sediment, and the water at the base, as well as interactions with the ocean at the ice sheet's margin. When ice reaches the ocean, it can form floating ice shelves, which are extensions of the ice sheet that float on the water but remain attached to the ice on land. Ice shelves can be hundreds of meters thick and can extend hundreds of kilometers from the coast. They buttress the ice sheet, slowing the flow of ice from the interior. If an ice shelf collapses or retreats, the ice behind it can accelerate, increasing the discharge of ice into the ocean. Several ice shelves in Antarctica have collapsed in recent decades, most notably the Larsen B ice shelf on the Antarctic Peninsula, which disintegrated rapidly in 2002. The collapse was preceded by warming in the region and by the formation of meltwater ponds on the surface of the ice shelf, which may have contributed to its breakup. The loss of the Larsen B ice shelf was followed by an acceleration of the glaciers that had been feeding it, confirming the buttressing effect. This raises concerns that other ice shelves, particularly those fringing the West Antarctic ice sheet, could be vulnerable to future warming. The West Antarctic ice sheet is considered particularly unstable because much of it rests on bedrock that is below sea level and because the bedrock slopes downward toward the interior of the ice sheet. This configuration makes the ice sheet susceptible to a process called marine ice sheet instability, in which retreat of the grounding line, the boundary between grounded ice and floating ice, can become self-reinforcing. As the grounding line retreats into deeper water, the ice becomes thicker and the discharge increases, driving further retreat. Models suggest that parts of the West Antarctic ice sheet may already be in irreversible retreat, though the timescale over which this retreat will occur is uncertain, ranging from centuries to millennia. The Greenland ice sheet, while not thought to be as vulnerable to rapid collapse as the West Antarctic ice sheet, is also losing mass at an accelerating rate. Warming air temperatures have increased surface melting, and warmer ocean waters have accelerated the melting of outlet glaciers where they meet the sea. The combination of increased surface melting and increased discharge from outlet glaciers has driven a net loss of mass from Greenland, contributing to sea level rise. If the entire Greenland ice sheet were to melt, it would raise global sea level by about 7 meters. If the entire Antarctic ice sheet were to melt, it would raise sea level by about 58 meters. Neither of these scenarios is likely to occur in the near future, but even partial melting involving a few percent of the ice would raise sea level by meters, with profound consequences for coastal populations. The connection between the Ice Age cycle and the current fate of ice sheets is direct. The ice sheets of Greenland and Antarctica are remnants of the last glacial period. When the climate warmed at the end of the last glaciation, most of the ice sheets that had covered the northern hemisphere melted, but the Antarctic ice sheet survived, and a much reduced ice sheet remained in Greenland. These ice sheets persisted because the climate in those regions remained cold enough to prevent complete melting. They are in a state of approximate balance, gaining mass from snowfall and losing mass from melting and iceberg calving, with the two roughly equal over long timescales. But as the climate warms due to human-driven greenhouse gas emissions, this balance is shifting. Melting and discharge are increasing while snowfall is not increasing enough to compensate. The result is a net loss of mass contributing to sea level rise. The glacial cycles of the past show that ice sheets can grow and melt on timescales of thousands to tens of thousands of years. But they also show that abrupt changes are possible. The rapid warming at the end of the Younger Dryas, the abrupt cold events during glacial periods, and the collapse of ice shelves during deglaciations all demonstrate that the ice in the climate system can change quickly when pushed past certain thresholds. This is a source of concern for the future. While models generally predict that ice sheet melting will be gradual, occurring over centuries, there is a possibility of faster, more abrupt changes that current models do not fully capture. This uncertainty is one of the reasons why predicting future sea level rise is difficult. The most recent assessments by the Intergovernmental Panel on Climate Change project sea level rise of roughly 1 meter by the end of the 21st century under high-emission scenarios, with larger rises possible over longer timescales. But these projections come with substantial uncertainty, particularly regarding the contribution from ice sheets. The interplay between the slow, predictable variations of Earth's orbit and the complex, sometimes abrupt responses of the climate system is central to the story of the Ice Age cycle. The orbital variations are regular and calculable. They can be predicted far into the past and far into the future with precision. The climate response, however, is not simply proportional to the orbital forcing. It is nonlinear, meaning that small forcings can produce large responses. And it is history-dependent, meaning that the state of the climate system at any given time depends on its past evolution. This makes the climate system difficult to predict in detail, even when the forcing is known. One of the ways scientists test their understanding of the climate system is by using climate models to simulate past climates and comparing the results with observations. If a model can successfully reproduce the timing and magnitude of past glaciations, the changes in temperature and ice volume, the variations in carbon dioxide and other greenhouse gases, and the abrupt events that punctuate the record, then there is more confidence that the model can be used to predict future climate. Many such simulations have been performed. And while models can reproduce many features of the glacial cycles, discrepancies remain. The 100,000-year cycle, the abrupt events, and the precise timing of deglaciations are not always well reproduced, indicating that there are still gaps in our understanding or that the models are missing important processes. One of the challenges in modeling Ice Age cycles is that the models must include representations of multiple components of the Earth system: the atmosphere, the ocean, the ice sheets, the land surface, and the carbon cycle, as well as their interactions. Each of these components is complex, and each requires detailed physical equations and parameterizations of processes that occur on scales too small to be explicitly resolved. Ice sheet models, for example, must account for ice flow, which depends on the temperature, thickness, and stress within the ice, as well as the properties of the bed beneath the ice and the presence of water at the base. Ocean models must represent circulation, mixing, heat transport, and the exchange of gases with the atmosphere. Carbon cycle models must represent the uptake and release of carbon by the ocean and the land biosphere, as well as the chemical reactions that govern the partitioning of carbon between the atmosphere, ocean, and sediments. Coupling these models together and running them for tens of thousands of simulated years is computationally demanding. Despite these challenges, climate models have become increasingly sophisticated and realistic. They have been used to explore a wide range of questions about the Ice Age cycle, including the role of different feedbacks, the sensitivity of the climate to orbital forcing, the mechanisms that trigger deglaciations, and the potential for abrupt changes. One key result from these models is that the carbon cycle feedback is essential for reproducing the magnitude of glacial-interglacial temperature changes. Without the reduction in atmospheric carbon dioxide during glacial periods, the cooling would be much smaller. This underscores the importance of understanding the carbon cycle and the mechanisms that regulate atmospheric carbon dioxide. The carbon cycle on glacial-interglacial timescales is primarily controlled by the ocean. The ocean contains roughly 50 times more carbon than the atmosphere, and small changes in the way carbon is distributed within the ocean, or in the rate at which carbon is exchanged between the ocean and the atmosphere, can have large effects on atmospheric carbon dioxide. During glacial periods, carbon dioxide is lower, which means that the ocean was storing more carbon. Several mechanisms have been proposed to explain this. One is that changes in ocean circulation alter the upwelling of carbon-rich deep water, keeping more carbon in the deep ocean and reducing the amount released to the atmosphere. Another is that the formation of sea ice around Antarctica reduced the area of ocean in contact with the atmosphere, limiting gas exchange. Another is that changes in the productivity of marine phytoplankton, driven by increased iron fertilization from dust, enhance the biological pump, transporting more carbon to the deep ocean. Iron is a micronutrient that limits phytoplankton growth in large parts of the ocean. During glacial periods, atmospheric dust concentrations were much higher, as indicated by ice cores, and much of this dust came from exposed continental shelves and deserts. When this dust settled on the ocean, it delivered iron, which could stimulate phytoplankton growth. More phytoplankton means more carbon taken up from the surface ocean, and, through sinking particles, transported to the deep ocean, effectively removing carbon from the atmosphere. This is known as the iron hypothesis, and it has been supported by experiments and models, though the magnitude of its effect is debated. Another factor that may have contributed to lower glacial carbon dioxide is changes in the alkalinity of the ocean. Alkalinity is a measure of the ocean's capacity to neutralize acids, and it affects the partitioning of carbon between dissolved carbon dioxide, bicarbonate, and carbonate ions. Changes in weathering rates on land, changes in the deposition of calcium carbonate in ocean sediments, and changes in the input of alkaline material from continental shelves all could have altered ocean alkalinity and affected atmospheric carbon dioxide. Disentangling the relative importance of these various mechanisms is an ongoing area of research. What is clear is that the carbon cycle is tightly coupled to climate on glacial-interglacial timescales. Carbon dioxide varies in lockstep with temperature, as shown by ice cores. This tight coupling is one of the reasons why climate sensitivity can be estimated from the glacial-interglacial record. The change in radiative forcing from carbon dioxide and other greenhouse gases during the transition from glacial to interglacial conditions is roughly 5 watts per square meter. The change in global temperature is roughly 5 degrees Celsius. This implies a climate sensitivity of about 3 degrees Celsius per doubling of carbon dioxide, consistent with other estimates. This is not a precise calculation, because the glacial-interglacial transition also involves changes in ice cover and other factors that contribute to the radiative forcing, but it provides an independent check on climate sensitivity derived from other methods. The close relationship between carbon dioxide and temperature raises a chicken and egg question. Does carbon dioxide drive temperature, or does temperature drive carbon dioxide? The answer is that both are true. Orbital variations change the distribution of sunlight, which directly affects temperature in certain regions and seasons. This temperature change can trigger feedbacks, including changes in ice cover and changes in the carbon cycle, which alter atmospheric carbon dioxide side. The change in carbon dioxide then acts as a global amplifier, spreading the initial regional temperature change across the planet and through the seasons. So the initial trigger is orbital forcing, but carbon dioxide is a critical feedback that amplifies the response. This is why the Ice Age cycle involves the entire planet, not just the high northern latitudes where the orbital forcing is strongest. The discovery of this tight coupling between dioxide and temperature has profound implications for understanding current and future climate change. The same mechanism that amplified orbital forcing during glacial cycles is now amplifying human-caused warming. By increasing atmospheric CO2, humans are not only adding heat-trapping gases to the atmosphere, but also triggering feedbacks that will further warm the planet. Some of these feedbacks are well understood and well quantified, such as the water vapor feedback and the ice albedo feedback. Others are more uncertain, such as feedbacks involving clouds, which can either amplify or dampen warming depending on their altitude, thickness, and other properties, and some feedbacks operate on long timescales and are only beginning to manifest, such as the release of carbon from thawing permafrost or the potential release of methane from ocean sediments. Permafrost is ground that remains frozen for at least 2 consecutive years, and it is found in high-latitude regions of the northern hemisphere. Permafrost soils contain large amounts of organic carbon, the remains of plants and animals that accumulated over thousands of years and were frozen before they could fully decompose. As the climate warms, permafrost is thawing, and the organic material is beginning to decompose, releasing carbon dioxide and methane. Methane is a much more potent greenhouse gas than carbon dioxide, though it has a shorter lifetime in the atmosphere. The amount of carbon stored in permafrost is estimated to be roughly twice as much as is currently in the atmosphere, so even a small fraction of this carbon being released could significantly enhance warming. The rate and magnitude of carbon release from permafrost is uncertain, depending on the rate of thawing, the availability of oxygen for decomposition, and other factors. But it represents a potentially significant positive feedback. Methane hydrates, also known as clathrates, are another potential source of feedback. These are ice-like solids in which methane molecules are trapped within a cage of water molecules. They are stable at high pressure and low temperature, and they are found in ocean sediments and in permafrost regions. If the ocean warms or if permafrost thaws, methane hydrates could dissociate, releasing methane. The amount of methane stored in hydrates is very uncertain, with estimates ranging widely, and the potential for large-scale release is debated. There is evidence from the geological record that methane hydrate destabilization has contributed to climate changes in the past, but the relevance to the current and near-future climate is unclear. These potential feedbacks add to the uncertainty in predicting future climate. The standard climate models used to project future warming generally do not include dynamic representations of permafrost carbon release or methane hydrate destabilization, because the processes are not well enough understood or because they are thought to be small compared to direct human emissions over the next century. But over longer timescales, centuries to millennia, these feedbacks could become significant, and they represent processes that could cause warming to continue even if human emissions are reduced. The Ice Age cycle, in its vast span and its intricate mechanisms, provides a framework for thinking about these long timescales. The cycle shows that climate is not static, that it responds to forcings, and that it has feedbacks that can amplify small changes into large ones. It shows that the Earth system has multiple states and that transitions between states can be abrupt. It shows that ice, carbon, and temperature are linked in ways that are fundamental to the planet's climate. And it shows that the system has a memory, a dependence on past conditions that influences future evolution. The current interglacial, the Holocene, has now lasted about 11,700 years. Previous interglacials, as recorded in ice cores and ocean sediments, have typically lasted between 10,000 and 30,000 years. Though there is variability, the interglacial, before the last glaciation, the Eemian, lasted roughly 15,000 years. The interglacial before that, marine isotope stage 11, lasted an unusually long time, perhaps 20 to 30,000 years, and it has been suggested as an analog for the current interglacial because the orbital configuration at that time was similar to the present. If the Holocene were following the pattern of previous interglacials, it would be expected to last for at least another several thousand years, and possibly much longer, before the climate began to cool toward the next glaciation. But human activity has changed this trajectory. The warming already underway, and the warming projected for the future, is likely to delay the next glaciation by tens of thousands of years or more. This means that the climate over the next several millennia will not be governed by the natural rhythms of the glacial cycle, but by the consequences of human emissions and the slow response of the Earth system to those emissions. Carbon dioxide will remain elevated in the atmosphere for thousands of years, even if all emissions cease, because the processes that remove carbon dioxide from the atmosphere, such as uptake by the ocean and weathering of rocks, operate slowly. The ocean will continue to warm and expand, raising sea levels. Ice sheets will continue to lose mass, contributing to further sea level rise. Ecosystems will continue to shift, adapt, or decline. The climate of the near future will be unlike the climate of the Holocene, and it may be unlike any climate experienced by modern humans. In the deeper past, millions of years ago, Earth had climates much warmer than the present, with higher carbon dioxide concentrations and no ice sheets. Studying those climates, Using geological and paleontological evidence provides some insight into what a much warmer future might look like, but the rate of change now is much faster than the rates of change in the deep past, and ecosystems and species may not have time to adapt. The combination of rapid change and human pressures such as habitat destruction, pollution, and overexploitation is already driving extinctions and ecosystem collapses. Understanding the glacial cycle and the current perturbation to it is part of a broader effort to understand how the Earth system works and how it will respond to continued human influence. The story of the Ice Age cycle is a story of discovery, of observation and measurement, of hypothesis and testing, of gradual accumulation of knowledge. It is a story that began with observers noticing boulders in the wrong places and scratches on bedrock, and it continues today with satellites measuring the height of ice sheets, with ships drilling cores from the seafloor with instruments measuring the composition of the atmosphere, and with supercomputers simulating the climate. It is a collective human endeavor, driven by curiosity and the desire to understand the world. And it is a story that has direct relevance to the present and the future, because the mechanisms that drove climate in the past are still operating, and because humans are now a part of the system, influencing it in ways that were unimaginable even a few generations ago. The rhythm of the ice ages, the slow advance and retreat of ice, the oscillation between cold and warm, is a fundamental feature of Earth's recent history. It is a rhythm set by the heavens, by the slow wobble and tilt of Earth's axis, and the slow variation of its orbit. It is amplified by the Earth itself, by the reflective ice, by the greenhouse gases, by the oceans and the land, and it is now being interrupted, perhaps for a very long time, by the actions of a single species. This is both a profound responsibility and a profound challenge. We are inadvertently conducting an experiment with the planet, changing its atmosphere, its climate, its ecosystems, in ways that will persist for millennia. The knowledge gained from studying the Ice Age cycle, from understanding the past, is essential for navigating the future, for anticipating the consequences of our actions, and for making informed decisions about how to manage our relationship with the planet. The ice will not return, not for a very long time. The interglacial will continue extended far beyond its natural duration. The world will warm, the ice will melt, the seas will rise, ecosystems will shift, species will migrate, some will adapt, some will disappear. Human societies will face challenges, from sea level rise to changes in water availability to increased extreme weather. But humans are also adaptable and resourceful. The same intelligence and ingenuity that allowed us to discover the Ice Age cycle, to decipher the climate of the past, to understand the forces that shape the planet, can be applied to managing the future, to reducing emissions, to adapting to changes that are already underway, to preserving the diversity of life and the habitability of the planet. The glacial cycle, in its slow majesty, its vast scale, its intricate feedbacks, is a reminder that Earth is a dynamic, interconnected system, that climate is not fixed, and that small changes can have large consequences. It is a reminder that the present is a moment in a much longer story, and that the choices made now will shape that story for millennia to come. The ice lies beneath the surface of Greenland and Antarctica, a remnant of the last glaciation, a witness to the cycles of the past. It is melting now, faster than it has in thousands of years, and the water it releases is changing the world. The story continues, and we are now a part of it.